Hello everyone. I think I've met some of you before during our last presentation. But today I will give a very different talk. It's mainly about practical tricks on data science competition. And to be honest, it's very hard to squeeze everything in a 20 minutes talk. I intentionally split this talk to two parts. This is the first, I call it the basic part. And as you may know, I am a senior machine learning developer in one of the best companies in the town. Thank you. You're welcome. In the world, okay, yeah. And I officially started my PhD yesterday. But actually, I have been working with my supervisor for almost 1 year. So first, I want to give credits to these great Kagglers. The first one, he's from Beihang University in China. And Raider, I don't really know where he's from, but I borrowed some of the materials from one of his previous talk. And yeah, I think SpongeBob is a Kaggle master, and Raider is the grandmaster, one of the around 100 grandmaster in the world. And this is me. Feel free to connect me on LinkedIn. So I'm also a Kaggle Competition Master. Currently, I'm ranking at 300-ish. I'm quite lazy recently, so I dropped a little bit. You see my highest rank is slightly higher. And you can also see me on GitHub. So sorry about using like 10% pages to introduce myself. So first, let's talk about what is Kaggle to make sure everybody's on the same page. So Kaggle it's mostly known as a data science competition platform, but actually it's also a very great place to find your data set. For example, you have some awesome algorithm, you have a great idea, but you don't have a data set, just go to Kaggle, they have a data set page. It's very easy to find a wide range of data sets. It covers like images, speech, text-based. You want to find like a toxic commons data set, there is such a data set. You want to find a cat and dog image data set, there are a few. And I think it is acquired by Google in 2017, so now they have I would say a sufficient amount of GPU resources you can leverage. Even if you want to run yourself some of your own experiments, you can use Kaggle. They provide you, I think, P100 graphic card, which is actually very expensive if you want to buy it by yourself. And they're free to use on Kaggle. So why Kaggle is fun? I think the last one is the most important one. So Kaggle Competitions has prizes. This is a screencast from one of the previous competition I was involved. This is kind of an average prize money you can get by entering the top 3 or 5. I was 8, sorry. I think a larger prize is from National Security Department in the States. They offered $1.5 or $1.3 million as the final prize. Okay, go back to the first item. Real-time standings. So Kaggle competitions all have a leaderboard. You can see the performance of all the other competitors. I do have experience about I was at, say, 100-ish, and after one night, I'm 200-ish. So this kind of forces you to keep practicing, keep improving your solutions to get a better performance. And you can definitely cooperate with others. There are 2 million registered users. Let's say they're all data scientists or data engineers. So you can cooperate with them, discuss with them, compete with them. And one of the greatest things on Kaggle is they have discussion forums and the kernels. So sometimes when you barely start to do, say, data science competition, or you barely start to learn data science, it's very hard to start because you don't really know how to start a project. But in the kernel, in the discussion forum, you can easily find a lot of people, they gracefully publish all their code base, all their ideas. In some of the competitions, if you leverage those resources, you can even enter top 20 on the leaderboard. And you can definitely learn a lot. And you will have a profile, the data science profile. Let's say this is data science version of GitHub. at least when someone came to our company, if he has such a promising data science competition file, it will be a big plus, I think. Yeah. And how does Kaggle works? So usually in our real-world problem, you won't have this setting, but in the data science competition, you will have two data sets. One is training set, one is test set. And the test set will have two splits. One is public test set and a private test set. So the leaderboard, during the competition, the leaderboard will show your performance on the public test set. So you will not have access to the private test set, even after the competition. So the final competition performance is decided on the test set, a private test set. So Kaggle competitions are usually covers a wide range of topics, from, let's say, conventional data mining, like predicting the click-through rate for some website. You want to predict house price in Los Angeles or something like that. They also have image competitions like classification, whether it's the image or dog or cat, the simplest case. You want to detect objects in the provided video or image sequences. You can also do image segmentation in, say, medical image or some other situation. So there are non-structured data. The only structured data you can get is in the conventional data mining competitions. There are also audio and signal competitions. I think several months ago, there's a very good signal analysis competition. They have some power line fault detection competition. So they basically receive sensory data from the power line, and you try to find when there were some fault cases. Natural language processing. It could be Quora duplicate question detection or toxic comment detection. There are a few recent competitions, like the first one, Jigsaw, unintended bias in toxicity classification. This is the toxic comment competition, and you can see there is a wide range of different topics. So we will go through a few tricks one by one, start from feature engineering to model evaluation. This is basically the life cycle of your ML project or the process of building your ML models. So first, there are two types of features, categorical and numerical features. Let's start with categorical features. One of the most common thing to do with categorical features is one-hot encoding. I think that's a machine learning 101. Basically, you create a bag of words for your categorical features and assign 0 and 1 values to the feature. And you can also do label encoding. Basically, for example, you have if you have a column which is country, and you have Canada, US, China, India, you convert those labels to 1, 2, 3, 4. But there's one drawback with this encoding. For example, if let's just use this example, like China, India, US, Canada. You convert that to like 4, 3, 2, 1, for example. But when you convert this to a numerical value, actually, the country doesn't contain any numerical information. But you convert that to a numerical value, actually, you include some, let's say, noise information. And also, this will fail when you have new categories in your test data. So we can also leverage other methods to encode your categorical features. Say counting encoding. You can count the occurrence of the specific value in this column and change that value to that categorical feature to the value. For example, if there's 100 occurrence for the Canada, then you convert Canada to 100. You can also do hash encoding, which is not very common nowadays, I think. Category embeddings. So you build an autoencoder or autoencoder-like model to convert your categorical features to discrete, continuous vector embeddings. And you can also do likelihood encoding. This is very similar to count encoding, but I think it's better for the columns with a lot of null values. And also you will build interactions for your categorical features. So there's a story about a neural net. So some people claim that neural net are universal function approximator. Yes, they are. But the problem is this is a theoretically universal function approximator only. So in the real world, it's very hard to let the neural network to learn everything. So theoretically, a one-layer hidden neural network can learn everything, but practically it can't. So it's better to build the interaction features by yourself. So you can definitely build features like this. You have two columns, x1, x2, and you build an intersection over these two columns. And there's a few, I think, practical experience. And you will see numerical features as well. This is very common in, I think, in real-world problem. You can definitely leverage different like scaling and transformations on that. I want to highlight a few. For example, the rounding. Sometimes you don't want your numerical features have too much precision, like 10 digits after like 1.330347, something like that. You don't need that. You do want to drop some too precise information. And also you can consider to discretize the continuous variable. For example, you have some feature which is like say age. Someone is 23, someone is 24, someone is 63, for example. Sometimes you don't need to be that precise. You can discretize this to say 20 to 30 as one category, 40 to 50 as one category. So it depends on the use case. So for example, if you're handling a health-related project, I would say the younger people are usually more healthier. So this might be a key feature in your application. And you can still use interactions between numerical features. So again, if you have column x1, x2, sometimes you just divide x1 by x2 will give you a great boost. Definitely the model can learn this interaction, but remember the neural network or the models are just approximators, so they cannot get the exact result. And there are a few other techniques that you want to try, like you can get the row static aggregation features, and you can also do clustering based on in a single columns. And you can always try a few more combinations of these techniques. And one thing to remember is if you want to use tree-based method like random forest or gradient boosting tree, you usually don't need to do scaling. If you're using neural networks or linear models, you probably want to do the scaling. And let's start with some basic cross-validation techniques. So usually in the data science competitions, you will only have your training set available. I mean, the training set comes with annotations. So you split that training set to a training set and a test set, or a validation set. So you can do cross-validation on this by splitting this training set to, let's say, threefold, a threefold cross-validation, and you validate each fold. So in a threefold setting, you will have 3 validation steps, and you select model based on this. The reason you want to have a separate test set from your training set is you don't want to have a biased validation. So there's usually 2 strategies to do. Usually the first strategy is it's good to do a smaller data set, and the second one you usually want to use it in a large data set. There's no strict definition about large or small. It depends on the type of data set and the range of the different labels you will get in the test set. The first strategy is very simple. You do cross-validation on your training set, and then you validate the result on your own test set. And the second strategy is you validate each fold of the performance on your test set, and you get the average to select the best model or configuration. So how to split the data set? There are a lot of different techniques. I will just cover 3 basic ones. The first one is K-fold. This works fine when you have relatively equally distribute the label. For example, you have 8 or 10 different classes in your label. And you can group, and you want to split them in this way. But you can also use a stratified K-fold. And this works very well when you have an imbalanced annotation or imbalanced label. For example, you have 3 classes. And the first classes only have, let's say this is 10%. Let's say this is 10% of your data set, this is class 1. And maybe 30% is class 2, and 60% is class 3. So this is very unbalanced. If you just do a random K-fold split, you may have 2 less class 1 in your test set or in your validation set. So it will strictly affect your final performance. And K-fold for time series. Time series is a little bit more sensitive. So if you just do a common K-fold, you definitely have your leaky information in your training set. So you will never be able to see the future in a time series. So K-fold for time series, you can do it in this way. I think the figure is very illustrative. So you cut at some time point, and you do a train test split before this point. And you start from this cut type point, use this as your use all the data set between this time set as your training set, and you grab another test set from future data. So you can do the K-fold for time series in this way. Oh, and by the way, if you do any time series related competition and you see a very good performance on your model, usually you use the wrong split for your cross-validation. And as I mentioned, on Kaggle, there's a public test set, there's a private test set. So the first trick or the first principle you need to remember is don't overfit public test set. Because whenever you have an evaluation result on your public test set, you're kind of leaking information from this public test set because you overfit your model to this public test set. If you just see, okay, I got a higher score on public test set, then probably there's some randomness got your model to get a higher score on your public test set. But actually, it's generalized very bad. So this is an example. Like, for example, I have a gradient boosting tree or a random forest. When I have 200 trees, I got a public score 0.812, and the private is slightly higher. So as you see, when I increase the depth of the model, I get a better and better score on the public test set. But you will potentially get a lower score in the private test set. Because when you do this evaluation, or when you look at the matrix, this information is provided by a specific subset of the test set. You may potentially overfit to that one, although you don't really train on that test set. And bagging is important. That's the principle or trick 2. So in especially conventional data mining competitions, you do want to use bagging method, or you do want to use ensembling method. So this is a common bias-variance trade-off. So you always want to reduce the variance, because variance usually caused by overfitting, where bias is usually caused by underfitting. So in most of cases, you won't underfit. In most cases, you overfit. So the key principle in the computation or in the real-world project is you want to reduce the variance instead of the bias. So the simple case to do a bagging is you can just change the random seed in your model. This is a simple case. You can also increase randomness by setting some other parameters or hyperparameters in your model we will introduce a bit later. Okay, so actually my specialty is in computer vision application, but today I will mostly talking about tabular data or structural data. So in structural data, usually we have a list of possible or candidate models we want to leverage during the competition. The baseline is usually the regularized generalized linear model. So they are very good ensembling materials if you want to do stacking method which we'll introduce later. And XGBoost and Let Gradient Boosting Machine, they are two of the, I think these two are always the top picks for those data mining related competitions. Basically, there are different modified version of gradient boosting tree method. And neural network. So in the conventional tabular data computation, usually neural network cannot do very well. But there's a few Kagglers, they have deep beliefs in neural net, so they keep using that. But it has been proved that if you have a really awesome feature engineering, the neural network can also do very well. But usually it needs some ensembling because neural networks are just a single model. So usually you have a larger variance. And you can also use some other models like SVM or random forest. But usually now the competitions, people start with the top 3, or they even just start with XGBoost, gradient boosting machines. And I know there's some recent trend about AutoML, which is very convenient to us because we can just drop the data to the entire pipeline, and automatically select the best hyperparameters or the best configurations for the entire experiment. But on the competition and many other real-world application cases, when you have a super large data set, this is not very realistic. So we need to do the parameter tuning by ourselves. So this is a typical steps when we do hyperparameter tuning for XGBoost. So you want to start by selecting appropriate learning rate. Usually this could be 0.1 to 0.2. And you can change this progressively, of course. And you want to tax the maximum tree depth, because usually tree depth is I think that's a primary problem of overfitting. If you have if you don't have a limited depth for your tree, then the tree can perfectly overfit to your training set. So you want to tune this value at the beginning. Well, of course, all the values can be changed later, but usually I follow these procedures. And you want to introduce regularization to the leaf splits. For example, alpha lambda values, and also the leaf node size. Basically, this is the minimum number of training samples you will have at each leaf node. And you can then start to tune the randomness of each iteration. So you already know, I think you already know, in the random forest or the gradient boosting tree method, you subsample both the columns and the rows. So you subsample the data set, and at each split, you also subsample the feature space. So you also want to play with this randomness. Usually 0.7 and 0.7. 0.7 columns, 70% columns, 70% rows are a good starting points. And after you finish tuning those values, you probably want to start to play with your learning rate again. But there's no golden principles, so this is just an empirical pipeline. And of course, if there's no time limit or you have enough computational resources, you can definitely start to ensemble different models. This usually gives you a boost. A non-expert approach is, of course, gray search. If you have a cluster of GPUs or cluster of CPUs, you have supercomputer, well, you're welcome to use gray search. Although they are not a smart solution, I think. And you can also leverage Bayesian optimizing method. I think this is one of the most common techniques used in AutoML pipeline. You do Bayesian optimizing method. So this is basically, I think this stuck in the middle of the gray search and hand tuning. And let's talk a bit about model ensembling. So the model ensembling, there's different techniques. So I basically split them to two groups. One is voting, one is stacking. So voting can be as simple as a majority voting, and we will see This is majority voting. So you have 3 models. They make very different predictions. They have 80, 70, 60% accuracy, respectively. And you just do a simple majority voting, and you probably get a higher result. Again, there's no guarantee, but usually you will get a higher result. And you can also do average. Oh, and by the way, so majority voting is used for classification case only in this format. And you can also do averaging. Averaging can be used for classification, can be used for regression. For regression, it's very straightforward. For classification, you basically just average the probability you get for each sample. So if you have, say, n classifiers, you can get a simple average. So this is a weighted average. So you can start with just a simple average. You have equal weights for all of the predictions. But you do want to try to optimize this. You do want to try to optimize this by validating the different weights on your validation set. So some models may have better contribution compared to the rest. And in the computations, if you have, for example, if you have a model with 80% accuracy, you have one with 70% accuracy, you probably want to assign the weights based on their accuracy. You have a slightly higher weight. For your better model, you have a slightly smaller weight for your worse model. And you can also do stacking. This is not very common in industry because usually this is time consuming. And in some of the competitions, they even stacking like 200 models, which is not realistic in the real world. And usually it gives like 0.001 gain in your final performance, which is nothing for real world industry, but it's very important for the competition only. So stacking, the simplified version stacking is very simple. When you build your, say, 5-fold cross-validation model, you use your prediction over your so this, for example, the model 1, you have the 5th fold as your validation set, and the model 2, you have your 4th subset as your validation set. So you make prediction on those subset, and use the predictive value as a meta feature, combined with another model, train on the entire training set, as your stacking or a meta learner. So you make prediction based on this data set, this new meta data set. So stacking can be very time consuming because there could be like several hundred models, which we don't really want to do that in our data lab. But I know there's a few libraries like H2O. They do have this one-liner solution for stacking. Basically, this is a stacking classifier or stacking regressor, so you can use that. Usually give you a decent result, although they won't help you to winning the competition, but they can give you a good result. So there's usually a few tips you want to remember when you do ensembling. This is not stacking, this is ensembling. So you can do this in a greedy forward approach. So you start to build the ensemble library. First, you select, say, 2 or 3 of your best models on validation set, and you start to add the fifths. But you don't, if you have, say, 100, you don't know which to add. So you try to add one of them, one by one, and you iterate this process to examine the performance after adding this one extra model to your library. So after a few iterations, you may end up with, say, 20 models. So that could be your final model libraries. So this number, again, is decided by yourself. Usually, this is a magic number. But I'm pretty sure ensemble more models. So this is, I think this is similar to some models I learned from economic course. There's something called diminishing returns. So when you start to add more models, you get better and better result. But after some point, the more models you add, the lower performance you will get at the end. And there's also some tricks with evaluation. I'm not quite sure whether they are useful in our daily life, but I think I should include. Okay, so for example, we do have some matrix like F1 score or F beta score, which is we cannot really, like they are not really differentiable. For example, you're training a neural network. You want your loss function to be differentiable. Otherwise, you cannot do backpropagation. So this is Keras or TensorFlow implementation of F1 score. You will see this step, this rounding step, is basically if your prediction is 0.4, you round this to 0. If this is 0.6 or 0.9, you round it to 1. So this step function is not differentiable. So after doing this, you cannot do any backpropagation with this matrix because it's not differentiable. So we can simply convert this to a soft loss function by removing this round. And again, you want a higher F1 score, so you do a minus here. Sorry, it blocked. Yeah, but you will see the minus, 1 minus. So you want a higher F1 score, which means you have a better model. So 1 minus, you're minimizing this 1 minus F score value. So this is kind of soft loss. So it's help you to optimize your neural net or optimize your model directly towards your evaluation matrix. But I don't think in the real world we really care about F1 score. In real world, we usually care either precision or recall, and I think recall are commonly used for evaluation. And you can also optimize your threshold for multi-label problem. For example, this is some images I grabbed from one of the previous competition. So this is satellite image, a different format of satellite image. From, I think from a company called Planet. So this is Amazon forest. So you see each of the image will have different label. For example, the first one, the top left one, they have haze and primary, 2 labels. And the second one, they have agriculture, clear, primary, water, although I don't know where is the water, but they have multiple labels. So in the multi-label, multi-class classification problems, usually you won't have a very balanced label. You can check the histogram on the right. We only have, let's say, 2.5K haze image, but we have more around like 40K image with primary label. So when you train, say, a neural net with your, this unbalanced label, you will have a sigmoid layer at the end to give the probability of this image patch belongs to one of the category. Belongs to every category. So you may receive a vector of that match length, and each value is the probability you get this image belong to this label. So usually the most common class will have a larger threshold. For example, in a binary classification case, after the sigmoid layer, you get a probability from 0 to 1. Probably you need to do the threshold at 0.8. Like every value below 0.8 means this is not a primary label image. And all the prediction above 0.8 might be the primary label. But in the haze case, usually you want to decrease the value, decrease the threshold. Maybe anything above 0.1 should be a positive. Anything below 0.1 should be a negative. So this is very common, and I think this is a common sense in all the imbalanced multi-label problem. And you are expected to see very different thresholds for each of the class. You can think of this, you are building binary classifier for each class. And you will use a very different threshold for each of the class. And you can also optimize for the matrix. So imagine you have a problem setting which you have a target from 0 to 4, and 0 to 4 values are representing the severity of some disease. So this is ordinal targets. So 0 means no disease, 4 means basically the worst case. So they are ordinal. The numbers, you cannot simply treat this as a classification problem because 4 are indeed worse than 3. So they have this ranking or numerical meanings. So in this type of ordinal, you want to you want to treat this problem as a classification problem. As a regression problem. But when you do a regression, you get a continuous value or continuous target space. You may end up with, say, 3.6. But when you do evaluation, you don't want to evaluate 0.6 with 3. You want to do 3.6. You convert that to 4. So you can start to search the threshold based on the matrix. You can start by setting some default value. Say, okay, everything below 0.5, let's say that's 0. Everything above 0.5 and below 1.5, this is 1. You can use this threshold search again to optimize towards a specific matrix. And so Kaggle is a very good playground for hyperparameter optimization and stacking. So these techniques are not very useful in our daily job, but it's a very good place if you suddenly find a really awesome paper you want to examine that. Kaggle have a wide range of different topics, different competition, different data set you can examine with. It's very easy to find. You basically just use it as a data set Google, a Google of data set, yeah. And usually any solutions you get from Kaggle, like if they're top 10%, they are good with real-world business case, because mostly the top 1 or top 2%, they heavily use stacking, which is not very useful in our daily job. Yeah, any questions? Okay, so each competitions, they have very different settings. So usually it's a daily, like every day you have 5 submissions or 3 submissions. And if you team up with others, you share the submission. So you can submit, like, in 5 days you can submit 25 times? Yeah, and each day you have 5 submission limit. Then don't you learn your test set in the process? Sorry, what? Don't you learn your test set in the process? Usually we don't touch test set, right? We use only once. Mm-hmm. But when you are repeatedly tuning your model like that, probably you are going to learn your test set. You are teaching your test set. Yeah, that's the reason my first principle is don't trust your public test set evaluation, because you're kind of leaking information to your evaluation process. You use the information, you use the feedback from the public test set, right? So another tricks or another thing you do want to do when you do the competition is you want to probing the private test set. You want to think of the distribution of the private test set. So in some competitions, the label distribution are very different between the public and private data set. So you do want to make a guess on that. Yeah.
Do you have any strategies for selecting the number of folds in the cross-validation?
Okay, so it depends. Some competitions, they only require you to submit your final prediction CSV file. In that case, I think people tend to use 7 or 10. But if you're required to run all your scripts on the Kaggle kernels, they usually have a time limit. So it's really a case dependent. So people usually start with 5, I think, 5 or 7. These are most common numbers. I like 5. I prefer 5.
And what about in real-world scenarios?
I think in real world we usually use, it really depends on the volume of your data. Usually if that's a reasonably large data set, you probably don't even need cross-validation. You probably just simply split them to train and test.
Okay, so for multi-class, multi-level classification problem, suppose there are around 30 levels. So do we have to manually put threshold on every level, or is there any other way we can just bypass that?
Yeah, so of course you don't want to do it manually. If you have 1,000 classes, it will kill me, right? So usually you can just, it's very simple. It's very not simple. I mean, it's very similar to when you try to plot the ROC curve. So you search from through different threshold, and you can plot the same thing for each of your class.
You had mentioned that you do some data pre-preparation before training your model, right?
Mm-hmm.
Like averaging and all. So how do you decide like till how much range should we take? So age could be in the range of 10, but suppose if it is let's say salary or something else, so the data could be there would be a lot of variety. So how do you decide that you should consider that?
Okay, so I think the question is how to decide the value or the range to discretize the continuous variable, numerical variable. This is one of the artist point in feature engineering. So there's no principle you can follow. It really depends. For example, if you're doing a health-related problem, you may want to use the official definition from Health Canada to say, okay, this is the YOS, this is the like the middle generation, this is the outer generation. So you may want to use this type of values. And if you want to do this is a guess. I don't have any experience with banking information, but if you want to predict the bankrupt probability of a person, usually I think the young people are more easy to be bankrupt because they don't have a lot of savings. So it's really the case dependent thing when you decide the range. Yeah.
More from the business perspective of Kaggle, when would a business not use Kaggle? Like, when is it a bad idea to use Kaggle as a business? Because it seems pretty great. You get like top data scientists, you get thousands of them looking at your problem. It seems like a perfect solution. Why would they choose Why wouldn't you choose when would you choose AltML? When would you choose Kaggle?
That's a tough question, especially when Martin's here, huh? So
It's very easy.
no, actually, I think most of the company, when they come to Kaggle, so they have to have their data set. So usually what Kaggle do is help them to format their data set to framing the problem, which is very similar to what AltML can do. But the Kaggle definitely have the biggest advantage is share. You can expose your problem to all of the world. And as I mentioned, usually the winning solutions, they are a stacking of 200 models, which is not realistic. So I believe most of the companies, they do want to pay attention to the discussion forum, to the kernel forum, because a lot of people will do a lot of EDA on the data set, which is actually worth more from a business point of view, because we don't I think our clients usually they really don't care about whether the model can be 89% or 80% accurate, but they do want to know the insight behind the data. So I think this is a benefit when most of the company came to Kaggle. This is the best benefit they want to get. They have several thousand data scientists helped them to explore this data set, which is we only have like 50 people in the company. We won't have 50 people work on the same projects, right? So we will have a small team. So this is the benefit if you come to Kaggle. And by the way, Kaggle is very expensive. So if you want to host a competition on Kaggle, usually it costs you like 0.5 million. It could cost, yeah. So to host the competition, usually they ask for like 200K to 500K. Yeah. Wow.
There is also the biggest problem in any data science, the problem definition. And Kaggle, you have to come up with a problem, you have to define it. It's not like in real world companies do not know how to define the problem. Their data is very dirty and they don't know how to work with that data. So typically what we're getting dump of a data set and some business use case, and we have to find what is actually the target, how to label that data, how to define the problem, and then how to build that and how to integrate that model with the business processes.
Yeah, and Kaggle usually
It's cheaper.
yeah, and Kaggle they usually don't accept like super dirty data dumps, so they need you to process that for them, and you basically know what data are needed for your problem. But a lot of companies they don't know this, so they come to us.
The target, like in my own experience, like the target can change based on the insights that, after going through the data set and, the different model iterations, like the target can change.
Yeah, like that's typical. There's the iterations and then feedback, getting domain expertise from the people working. There's also privacy of the data. In a lot of places, like you cannot share the data. We have customers where we cannot even have the data on premise. We have to VPN to their office, to VPN to their private cloud, and we cannot even look.
Yeah, there's actually a significant drop of number of competitions after Google acquired Kaggle, because now Google is behind Kaggle. So the competitors of Google, they don't want to expose their data to Kaggle anymore. Yeah.
So my understanding is that when you try to implement a neural network, you have the choice of performing normalization and just scaling on your training data.
Mm-hmm.
So when you try to make prediction, you actually put your training data, put test data through the same process of normalization and just scaling.
Yep.
However, back in the case of stacking, I see that you put your your data through multiple model, and then you have this new feature. So my question is, so when you try to make a prediction, how would you process your test data to feed into this model?
So the question is, when you use, say, the 6 models, first 5 models, they have different statistics for the training set, and the fifth. So basically, when you make prediction in your stacking system, you reuse all the scale transformers or the scalars during the training. For example, when you want to get this part of your meta feature, which is this one, you use the same scalar from this model. Use as the exact same scalar as the model 1. So you do the same thing for everyone. When you do cross-validation, your scalar statistics should be only based on your training set. For example, the statistics should be only on the first 4 splits. And for the model 2, the scaling statistics should only come from the first 3 and the last one. Similar works for the rest.
Basically, you've got to apply the same 5 contain 5 different times to our test data to feed into the model.
Sorry, I didn't quite get the question.
So basically, what you're saying is that we got to process our test data 5
Mhm.
different times in the case of 5 different models
Yep.
in 5 different ways
Yep.
to feed into your model
Yeah.
state.
Yeah, that's also increased the. I think this also increased the variance through between different models. So the more diverse your models are, usually the better ensembling performance you get. Yeah. So you basically apply, in this case, you apply 6 different scalars to your test set. Alex? Oh, yeah, sure.
You talked a lot about the technical side, but I'm also curious. I know a lot of teams that win Kaggle competitions often recombine teams or
Mhm.
sort of pick models from other groups and combine in
Yeah.
some fashion. Do you have any strategies for how to go about teaming
Okay.
up with other people in
Yeah.
Kaggle?
So when we team up with others, we usually, the first thing we need to try is we just ensemble our models. So as I mentioned, usually the larger diversity you have in your model libraries, the better performance you get after the ensemble. So for example, if we two are doing competitions and I'm using neural net, you're using a gradient boosting machine, usually we believe that our group will be better. So, but if, say, you're using neural network, and I'm also using neural network, like our learning capacity and the model will be relatively similar. So usually this will result in a relatively smaller performance boost. But there's no golden rules, sorry.
So I was working on a problem, and it has around 250 features, out of which around 120 was categorical variables. Some were nominal and some were ordinal. So when I converted it to one hot one vector encoding, the features just exploded. It was around 1,000 features. So then when I tried to train it, it just overfitted. So what are the ways that we can reduce features?
Usually in that case, so this is a very common case in recommender system. So for example, I want to check what type of music I listen to and my friends are listening to. So okay, I listen to one song from Michael Jackson, he listened to one song from Rihanna, and say there's 1 million different sounds. So you will get super sparse feature space. So you can either build autoencoder-like models to squeeze the feature space, or you can do factorizer machines, which is very commonly used in recommender system. But to be honest, I'm not an expert in that case. Yeah, but usually you want to reduce the dimension of your feature space in some way. Yeah.
Yeah, if there are any more questions, I hope G will join us for a drink. Are you?
Yeah.
Yeah, so you can ask in Mercer. And again, we don't have drink tickets, but we have a tab open, so.